All right, we have one more acid-base video to do here. This is the last and the third acid-base lesson, the compensatory responses. And in this one, I'm really going to sort of leave the compensatory responses alone. I want to talk a little bit about the relationship between potassium and acid-base problems. When you have hydrogen ions elevated, let's say in an acidosis, so they're more than the usual concentration of hydrogen ions in your plasma, you'll buffer some of that, okay, in the plasma, but remember you also have intracellular buffers that take care of some of that, and the intracellular buffers kick in when hydrogen ions move into the cell. Okay, so in order for this buffering reaction to take place, hydrogen ions are moving in. Well, the only way that that can happen is you're moving in a cation. The only way that that can happen is if you either move an anion in with it, so you maintain electroneutrality, or you move a cation out of the cell in exchange for the hydrogen ion. Okay, so high hydrogen ions in the plasma. You can move hydrogen ions in as long as you maintain electroneutrality. Well, what the vast majority of your cells do is when hydrogen ions move in, they move potassium out in exchange for it to maintain electroneutrality. And when you move hydrogen ions out, you move potassium in to maintain electroneutrality. Okay? So in the face of an acidosis, you're going to have hydrogen ions moving into the cell, and as they move in, potassium is going to move out. Well, that's helpful for regulating the pH, but if you're adding potassium to the blood, it can cause a disruption in your potassium balance. And specifically in this case, it can cause a hyperkalemia. So in acidosis, a drop in pH means potassium leaving the cells can cause an increase in serum potassium or hyperkalemia. And of course, you guys know if you get hyperkalemia, that means bad things for your excitable cells. Your resting potential rises, you cause all kinds of problems with the electrical responses in those cells, okay? Of course, in the face of an alkalosis, now your hydrogen ions are down in the serum, and you're going to get hydrogen ions that are dissociating from those buffers in the cells, and those hydrogen ions are going to move out into the plasma. And once again, that happens in exchange for potassium. So now, for an alkalosis, we have hydrogen ions moving from inside the cell to outside the cell. And as that happens, potassium moves in exchange for that into the cell to maintain electroneutrality. So now, with an alkalosis, you're getting the potential for a hypokalemia, where your blood potassium drops as your pH is regulated, okay? So again, hypokalemia, bad things, right, for excitable cells. So the kidney also produces in this process, participates here. So if you have an alkalosis, you're decreasing hydrogen ion secretion, okay? And what happens is, when you decrease hydrogen ion secretion, your excretion of potassium increases. So here's our system, if you might remember, and in our collecting duct, a lot of the hydrogen ion here is being secreted and in exchange for potassium ions. So in the face of an alkalosis, we've decreased the secretion. That means we've decreased the reabsorption of potassium. So you've got hypokalemia as a result of the alkalosis, just because of the exchange from the cells in the body. And this adds to the problem by reducing potassium reabsorption. Okay? And so this exacerbates your hypokalemia. Okay? So, and of course the opposite happens with acidosis. All right, so basically a pH change of 0.1 causes a change in potassium in the opposite direction of the pH change, 0.7 millimoles per liter. So as you can see, if you drop, if you drop a tenth, an increase in 0.7, that ain't good. If you drop more than that, it's going to be really not good. Okay, so this can produce a rather serious hyperkalemia. All right. So the opposite is also true. If you have hypokalemia for some other reason, potassium is going to move out of the cells because you're going to have low potassium in the plasma. Potassium will move from inside the cells to outside the cells, and as that happens, hydrogen ions are going to enter the cells, and so you can get metabolic alkalosis in response to a hypokalemia. Okay. In this case, this is the primary problem, and this is something that results from that primary problem. And once again, our kidneys exacerbate the problem. During a hypokalemia, you're going to reabsorb as much potassium as you can, and what that means is that you're going to be excreting a lot more hydrogen ions, and so this is going to make your metabolic alkalosis work. And of course, as you secrete more hydrogen ions and excrete more hydrogen ions, you're producing more bicarb. That's contributing to your metabolic alkalosis. So this adds to the problem, and once again, here we are. You're producing more bicarb as you secrete more hydrogen ions, and you're doing that because you're reabsorbing more potassium in exchange for that. Okay? So the kidneys make this worse. Okay. So something to remember, anything that affects potassium balance can affect the acid-base balance. And so something like inappropriate aldosterone secretion, loss of body fluids that are high in potassium, like sweat or vomit or diarrhea, insulin excess or deficiency, all these things can disrupt your potassium balance, and they can cause an acid-base imbalance that will go along with that, okay? Because potassium is being exchanged for hydrogen ions during these problems, all right? I'm going to end this here. There are some practice acid-base problems with answers in the lesson notes. I strongly suggest that you go through those. The answers are really extensive, so hopefully you guys will understand the answers and they'll make sense to you. And once again, in relation to this, I do strongly encourage you to come to the A-based computer lab. That will add some additional problems that should really help increase your understanding of this material. Okay? Thanks for your time. I'll see you guys in the rooms.